Hey guys, it's Miss Cassano, and today we have a video on reviewing solving systems of equations with two variables. Now, this is a topic all the way back from Algebra 1, so I am asking you to dust off some cobwebs. Just like last time, take out your video notes and follow along, and the rule is whenever I write, you write too. Before we start solving systems of equations, I want to talk about what it really means. So when we solve a system of equations, we're finding possible points of intersection. So I provided you with three graphs, and this is going to explain why I say possible points of intersection. There's three different outcomes that can happen when solving a system of equation. You can either get that these linear functions intersect at one point, so that would give you one solution. You could get that they intersect at no points, so that means that they're parallel lines, just like shown here. That would give you zero solutions. That would also be called an inconsistent system. So, zero solutions is an inconsistent solution. Or you can get something like this. And now, this last graph right here looks like a graph of one line, but it's actually a graph of two lines. They just happen to be the same line. So the amount of points of intersection of these two lines is infinite because these lines lay on top of each other. They go on forever and ever and ever, so they have all possible points of intersection in common. So they could have infinite. So when we're solving these systems of equations with two variables, we're looking for it either to have one point of intersection, no points of intersection, or an infinite amount of points of intersection. All the way back in Algebra 1, you learned two different methods for solving a system of linear equations. The first method was called the substitution method. The substitution method means that you would solve for one variable. So let's say I want to solve one of my linear equations for x. And then I would take whatever x equals and substitute it in to the other linear equation. A tip for using the substitution method is to pick the easier function to work with. So if I was going to start off solving this system of linear equations using the substitution method, I would pick to work with the x minus 5y equals negative 6 function. If I'm using the substitution method, my end goal here is to get this function in terms of one variable. And I can do that very easily. All I have to do is add 5y to both sides, and I got x equals 5y minus 6. I have x in terms of my other variable y, so all I'm going to do is take x and plug it back into the other linear function. So I took what I got in the first linear function, I got x equals 5y minus 6, and I substituted that in for x in the other function. Now I'm left with a linear function in terms of one variable, y. And we know how to solve this. All we have to do is just solve for y. So my first step to solve for y would be to distribute my 2. So I'd be left with 10y minus 12 minus 3y equals 9. I'm going to combine like terms. So I have a 10y here and a negative 3y here. That would give me 7y minus 12 equals 9. My end goal here is to get y by itself. So I'm going to add 12 to both sides. And I'm left with 7y equals 21. My last step to get y by itself is to divide by 7. So 21 divided by 7 leaves me with y equals 3. Now, I have my y value, and don't forget, when we're solving a system of linear equations, we're really looking for a point of intersection. So this is my y-coordinate of my point of intersection. Now, I have what y is, And I have x up here in terms of y. So all I'm going to do to get x is just plug back into that equation. So I'm going to substitute y back in. So 5 times 3 minus 6. 5 times 3 is 15 minus 6. So after substituting y into our equation for x, that is in terms of y, I'm left with x equals 9. So my system is x equals 9, y equals 3. So I get that this system of linear equations has a point of intersection at 9, 3. Now, I provided you with a graph just as a little check. And if we look at it, if I go to 9, 3, I have one point of intersection. So the other method that you learned in Algebra 1 is called the elimination method, and you do exactly what it says. You use multiplication to eliminate some variable, so it just is left in terms of one variable. So all I did was rewrite my two formulas, 2x minus 3y equals 9, and x minus 5y minus 6. So I am going to rewrite my top one, just so everything's in one place. And I think what I want to do is multiply my bottom equation by negative 2. So if I do that, I get negative 2x plus 10y equals 12. Now, because I'm using the elimination method, I did this on purpose. I picked a number that would allow me to eliminate my x variables. So 2 and negative 2 cancel with each other. So my x variable is gone for right now. I don't have to worry about it. Negative 3y and 10y combine to make 7y. And 9 plus 12 gives me 21. So I want to get y by itself. I'm just going to divide both sides by 7. And that gives me y equals 3. Now, I'm not done yet because, again, I'm solving for a point of intersection. I have to use this y value and plug it back in for x. So what's tricky about the elimination method is whatever function you manipulated, so I manipulated this bottom one here to be able to cross it out, you can't substitute y back in for. So you have to pick the other function. So I didn't touch 2x minus 3y equals 9, so that's the function I'm going to substitute in. 2x minus 3y equals 9. I'm going to substitute in 3 for y, so I'm here, 2x minus 3 times 3 equals 9. 2x minus 9 equals 9. I want to get x by itself, so I'm going to add 9 to both sides. And I'm left with 2x equals 18. Divide by 2, divide by 2, and I'm left with x equals 9. So again, I get that the answer to my system of this system of linear equations is x equals 9, y equals 3. Or, since we're solving for a point of intersection, I get that this system of linear equation intersects at one point at 9, 3. Now, is it strange that we got the same answer here as here? No, because we were solving the same system of linear equations. You better get the same answer. I'm just using two different methods that were shown to you in Algebra 1. We are going to do one more really quick example. So I gave you two more linear functions, and I know you can see the graph, and I know you know how this is going to end up. But I just want to show you what an inconsistent linear system looks like when you solve it algebraically. So you can use either method you want. I prefer to use the substitution method this time because they're giving me a function in terms of y already. So I'm going to rewrite my functions. Y equals 1/2 x plus 2, and x minus 2y equals 2. It's pretty clear why I'm using substitution. I don't have to do any extra work. I'm already given a function in terms of another variable. So everywhere I see a y, I'm going to substitute in this function. So x minus 2 times, well, I have a y here, so I'm going to input my function. 1/2 x plus 2 equals 2. So now I'm going to start solving for x. X minus, well, I'm going to distribute my -2. -2 times 1/2 x leaves me just with x minus 4 equals 2. So x minus x cancel with each other, and I'm left with -4 equals 2. Does -4 equal 2, or is that weird? Well, -4 obviously does not equal 2. And since we have this weird thing happening at the end, we know that this is an inconsistent function. This weird conclusion, inconsistent. Sorry, I had some technical difficulties. Since I get this weird conclusion at the end when I'm trying to solve for a variable, -4 equals 2, obviously we know -4 does not equal 2. So there is no point of intersection. So it's inconsistent. And obviously, when looking at the graph, we can tell that these two lines are parallel, and we know that parallel lines never intersect. So that's pretty much it for a review on a system of linear equations. We're going to do another practice one in class. Yeah, so I will see you in class tomorrow. Bye.